So, in the last video, we saw how the biological neural network for the Hebbian learning process is similar to the completely connected Ising model. Now, the question was that can we mimic this biological neural network for Hebbian learning or associative memory in an artificial way? So, as we had discussed, John Hopfield in the 1980s created this idea called as the Hopfield network, which we will discuss here quantitatively. So, the structure of a Hopfield network is something like this. We have a set of neurons which are completely connected to each other, like this. So, this is how the structure of the Hopfield network looks like, where these circles are neurons and these lines represent the synapses or the connections between the neurons. So if we have a Hopfield network, something like this, of four neurons, let's say capital N is equal to 4, where capital N denotes the number of neurons in the Hopfield network. And let's say y1, y2, y3, and y4 are the values of the neurons. Then these connections can be denoted by W12 or W21, W14, W41, W13, W24, and so on. So I can write a 4 by 4 matrix, weight matrix, to denote the strength between the neurons, and it will be something like this: W12, W12, W11, W12 to W14, W21, W22 up to W44. And these are the diagonal elements, where the restrictions on the diagonal elements is that they are equal to 0 and Wij is equal to Wji. So if I write the properties of these weight matrices in the Hopfield networks, then first of all, the weight matrix is a square matrix of the dimension n cross n. Second, that it is symmetric, just like this. Third, the diagonal elements are always equal to 0. And fourth, that all elements of the weight matrix are all real. So now that we understood how the synapses or the mathematical structure of the synaptic strength, let us understand how to find the value of the neurons. So we can denote the value of the neuron by something like this: yi, comma t, where t represents the value of yi, the ith neuron at time t, and I goes from 1 to n. Now, another thing which is important is that we are considering there is only one pattern. If there are more patterns, then I would write yi mu or something like that to denote I'm talking about which pattern. But let's consider for simplicity that we are just talking of one pattern being stored in the Hopfield network. Now the values of yi can be 0 or 1, or minus 1 and 1, and as we discussed, we will just consider this particular uh, convention. Now, how do we find the value of yi? So the value, depending that we know the weight matrices, then the value of yi at time t plus 1 is given as sine of ai, where ai is equal to summation I not equal to j wij yj at time t plus bi, where bi is called as a bias. We will understand what it is later on. And these w's and b's are not dependent on time. And the function sine is such that if there is a value x in it, so sine of x is equal to plus 1 if x is greater than 0, and it is minus 1 if x is less than 0. Let us look at one example. So we have an example. Let's say we have a Hopfield network of only two neurons, y1 and y2, and there is a connection between them. And we are considering at time t. Then the weight matrix can be given as W, which is equal to W11, W12, W21, W22. It's a 2 cross 2 square matrix. And let's say that it has a value like this, as it is symmetric also. And let's say that the bias is 0, and the values of the neurons at time t is equal to minus 1 and 1. So this is y1 and this is y2. Now let's say that I want to find the value of the neuron y2 at time t plus 1. Then it is given as sine of summation I not equal to j w I j y j plus bi, where I is equal to 2, where I is equal to 2. So I can write this as sine of w21 y1 plus b1, and this will give me the value as sine 1 into minus 1 plus 0 equal to sine of minus 1, which is equal to minus 1. So y2 at time t plus 1 is equal to minus 1. Similarly, I can find the value of y1 at t plus 1, and I leave it as an exercise for you. So these are the broad rules which a Hopfield network follows. Now that we have understood how the Hopfield network works and the rules associated to it, let us derive a few things and understand how it can store the memory, and also we can retrieve the memory from these by taking some examples. So we learned about the Hopfield network, the mathematical structure of the Hopfield network in the previous section. Now let us understand that we can associate a energy-like function to the Hopfield network, and we can play with it and try to understand this particular quantity which is can be associated to the Hopfield network. Let me define the energy of a Hopfield network as E y bar equal to minus summation I yi ai, where yi we already saw is the sine of ai, and ai is equal to summation I not equal to j, wij, yj plus bi. So this thing is nothing but the sign of ai, and this is ai. So the product of this is always positive and the energy will always be negative. So now let us try to reduce the form or simplify the form of the energy of the Hopfield network. So I can write this as, by replacing ai, I can write it as summation over I not equal to j, yi, wij, yj plus summation or minus summation I bi yi. Yep. So now let us try to simplify this even further by using the constraints of the weight matrix, that is wij is equal to wji and wii equal to 0. Let us say take an example of only two neurons. Then my ey bar can be written as minus y1 w12 y2 plus b1 y1 plus minus of y2 w21 y1 plus b2 y2 by using this particular formula. This is for I equal to 1 and this for I equal to 2. Now I can also write this particular right hand side in this manner by using the constraints on the weight matrix. So I will rewrite this in this manner. So this will be minus half y1 w12 y2 plus y2 w21 y1. You see that as w12 is equal to w21, this will become 2 times y1 w12 y2, and this half and half gets cancelled and we will get this particular bracket except this b1 y1 term. Similarly, I can write this term, this whole term as y2 w21 y1 plus y1 w12 y2. Again, we are using the symmetry. Now I can insert these two terms also freely, because as w11 is equal to 0, it's just there for uh, completion purposes. And I can also have this in this manner. Insert this particular uh, term without any repercussions. And I will collect all the bias terms. Now, if you look at this, I can write this entire matrix, the entire term, all the terms in short. So I can write this as E of y bar is equal to minus half summation I comma j is equal to 1 to n being equal to 2, yi, wij, yj minus summation I is equal to 1 to n biyi. So this is the form of the energy of the Hopfield network. However, if you consider a fully connected Ising model of spins, so we have a fully connected Ising model of spins where all these circles represent spins. I can write the energy of this particular model or the system as H equal to summation I comma j, sigma j, where sigmas represent uh, the direction of the spin, and usually it is just up or down, no other directions are included. And this is the magnetic field strength, this is the direction of the field, and the summation goes from 1 to n, the number of spins. This is for a fully connected Ising model. So we see that they look a lot similar, and this energy is the energy of the system at some time t. If I replace yi as yit, so this particular energy term will evolve over time. So the energy term will evolve over time and try to reach the minima. So if I plot the energy versus time, I will see that the energy of the system will monotonically reduce. It will try to reduce monotonically, and over some time, it will try to reach the minima and stay at that particular value. So this point, or when it reaches this minima, we can call it as it is the stable equilibrium point of the system. So this energy of the Hopfield network can be used to quantify if the system is reaching equilibrium point or not. So now let us learn how a Hopfield network can memorize something. So the whole idea about storing a pattern or memorization by the Hopfield network is actually to find the right weights which could define that particular pattern. Yes, I'll try to make you understand with a simple example. So let us say that we want to store a pattern like this in my memory. This is some image I want to store in my memory, and it is divided into four parts. And I name the cells as 1, 2, 3, and 4. And let's say that this particular cell, which is colored, has a value of +1, and uncolored has a value of -1. Then I can use a Hopfield network of four neurons. Let's say I have these four neurons to store this pattern. Let's say I denote the value of this first neuron by y1, this as y2, this as y3, and this as y4. And as this is a Hopfield network, all the neurons are connected to each other. So I can store this particular pattern in uh, this Hopfield network, and we can say that the value of the neuron y1 is +1. It denotes the value of it denotes that the cell 1 is colored. The value of y2 is -1, denoting that this value of the cell 2 is not colored, of 3 is not colored, and 4 is colored. So this value is +1, -1, minus 1, and plus 1. I can write this values or this Hopfield network, the values of the Hopfield network in a column vector y1, y2, y3, and y4 such that this is 1, minus 1, minus 1, and 1. So, as I said earlier, the whole problem of finding or storing a pattern is to find the right kind of weights. So you see that I have not defined what are the weights here. So the whole problem is to find the weights uh, of this particular Hopfield network. So how do we find it? If we find these weights, we can say, and we define a Hopfield network with these weights, then we can say that this particular Hopfield network has the memory of that particular pattern stored in it. So, according to our understanding of the Hebbian learning process, which we learned earlier in the part 1, if you recall, W, if I define it to be equal to some matrix yi, yj, the values of the matrix W as yi into yj for all I not equal to j and equal to 0 for all I equal to j. If I define the elements of the W matrix in such a way, then I can say that the pattern is stored in the memory in that particular Hopfield network. So in this previous example, we can say that the weight matrix is a 4 cross 4 matrix as there are 4 neurons, and the values of the diagonal elements are 0, and the values of the non-diagonal elements are as such, which we get by multiplying yi into yj. So this is y1 into y2. And because this matrix is symmetric, this is how the weight matrix looks like for that particular pattern which we needed to store. So what I would do is I will create a Hopfield network with these weights. So let's say this is 1, 2, 3, and 4. So as 1 2 is minus 1, 1 3 is minus 1, 1 4 is 1, and 2 3 is 1, 2 4 is also 1, and 3 4 is minus 1. So if I define a Hopfield network with these weights and I input some q to it, let's say this is a q that I give to the system. Okay, it's partially correct. This is not the pattern which we needed, but this is some q that I give to this pattern. This Hopfield network with these defined weights will eventually fall into this particular state. This is because of the weights that we have defined here. So the weights will remain the same over time. So yeah, so this is what how the weights should look like, and we can call this as the stable equilibrium point of this Hopfield network. However, here we are talking about of only one kind of a pattern stored in this Hopfield network of 4 neurons. We can store more patterns in this particular system. So let's say this pattern is denoted by p equal to 1. This particular pattern is stored in the Hopfield network. Now, if I want to store another pattern in the system, let's say I want to store a pattern like this in the system, and I give the value small p equal to this a name. Yeah. Then the then the weight matrices, in this case the elements of the weight matrix can be given as wij equal to 1 by capital P summation over all the patterns p yi p yj p, where for all I not equal to j, and it is equal to 0 as we already know. So this p is the total number of patterns. So here it is 2. That is, we wanted to store two patterns, and this small p denotes the name of that particular pattern. And yip, you can say, are the value of the ith neuron for the pattern p. Note now, there is a limit to how many patterns that can be memorized. There is a limit to how many patterns that can be memorized. You can check the paper by McAleese, where they show that the capacity of storage depends on the number of neurons. So it's something like 0.14 into the number of neurons in that particular Hopfield network. So you can see that in terms of the storage capacity, the Hopfield network is not very efficient. We need a lot of neurons to store. This also then gives us a motivation. Can we use quantum mechanics to improvise? We may see this in later videos. The other thing that should be noted is that there can be memory fusions in Hopfield networks if we are storing more patterns, more than one pattern. So there can be memory fusions when more than one pattern is memorized. So what I mean by the memory fusion is when recalling the emergent stable pattern would be a fusion of two stable patterns. So it can happen if I give some q. I'm not saying which q, but if I give some q, then the stable pattern could be a superposition of these two patterns that are stored inside the Hopfield network. I will not go into the detail of this, but you can let's say that this is the pattern 2. Then it can be that I would get a fusion of. So what would happen is that if I give some q, the system may fall into this over time as a stable equilibrium point. So such phenomena is unwanted, and there are such malfunctions in human memory too, that we recall. There are errors in our recalling. So I think that it is very well mimicking how the human memory works. We just saw how the Hopfield network would store or memorize a pattern. So we saw that it can be done when we define or we find out the ways, the weights of the Hopfield network for a stable pattern that we wanted to store. So we saw that the weight of the Hopfield network for a pattern like this to be stored in it was W equal to 0 -1 -1 1 -1 0 1 -1 -1 1 0 -1 and 1 minus 1 minus 1 0. We saw that this should be the weight matrix for a pattern like this to be stored inside the Hopfield network of 4 neurons, where we said that a colored pixel or cell will have a value of plus 1 and non-colored will have a value of minus 1. Now let us say that uh, to this particular Hopfield network, we give some q at time t equal to 0, and we want this particular q to fall to the stored pattern inside the Hopfield network. So let's say that this is the q that I give, or this is the pattern that I give to the Hopfield network, and it's kind of a rough memory that I am giving to the Hopfield network, and I want the Hopfield network to give me the output of the stored pattern inside it and correct this particular q. So this is the stored pattern as we saw earlier. And the weight matrix we just saw for this kind of a stored pattern we just saw is this. Is the weight matrix for it. So I give a q like this. So if this is the q, the y matrix at time t equal to 0 is equal to 1 minus 1 minus 1 minus 1. And the y matrix of the stored pattern is 1 minus 1 minus 1 1. We just already saw this earlier also. Now let's say that I give this q at time t equal to 0, and I want this particular Hopfield network over the time and iterations to fall to this particular pattern and stay in this particular form for all the later time. So let us start and see that if this is the weight matrix for the Hopfield network, the q will eventually fall here. So let's say that let us find the value of y1 at time t equal to plus 1. That is the first iteration. So this is nothing but sine of summation I not equal to j wij yj plus bi. We saw that we'll consider this to be equal to 0. So this is sine of minus 1 into minus 1. So as this I is not equal, as this I is equal to 1, we will consider v w 1 w11 equal to 0. We will not consider j equal to 1. So let's start with w12, and this is the value of y. Um this is the value of y1, y2 at time t equal to 0. Let's write 0 also over here. So this is the value. And then similarly, we will just expand this summation. So this will be equal to sine of 2 minus 1, which is equal to sine of 1. And we will see that y1 is at time t equal to 1 is plus 1. Similarly, we will see that y2 at time t equal to 1 is sine of minus 1 into 1 plus 1 into minus 1 plus minus 1 into minus 1. And this will be something like sine of minus 2 plus 1 equal to minus 1. Similarly, you will find the value of y3 at time t equal to 1 to be equal to minus 1, and y4 at time t equal to 1 equal to plus 1. I leave it as an exercise for you. So we will see that the y matrix at time t equal to 1 is 1 minus 1 minus 1 and 1. This corresponds to the pattern something like this. But this is what was the stored pattern inside the system. So we saw that if we started with a queue like this at time t equal to 0, the Hopfield network with the defined weights earlier will fall to this particular form. Now let's see if it will remain in this particular stored pattern form for all the later time. So now let us find the value of the y matrix at time t equal to 2. That is the second iteration. Now if you do this again, we will see that y1 at t equal to 2 is sine of 1 plus 1 plus 1, which is equal to 1. I get this 1 from using this weight matrix. In this weight matrix and this y. Now, instead of y0, I use y1. So it will be minus 1 into minus 1 minus 1 into minus 1 and 1 into 1. So this becomes equal to 1 plus 1 plus 1 is equal to 1. Similarly, I will find y2 at time t equal to 2 equal to minus 1, y3 at time t equal to 2 equal to minus 1, and y4 at time t equal to 2 is all equal to 1. Now this will correspond to the pattern. This y matrix corresponds to this particular pattern, which is the same pattern as we saw earlier. So we see that as the time progresses, the system will remain in this particular uh, pattern. So we see that this is the stable equilibrium point of the system. And the Hopfield network will remain in this particular stored pattern for all the later time. Now, let us see what happens to the energy of the Hopfield network. So, the energy of the Hopfield network we saw as earlier was defined by this particular quantity E of y bar at time t equal to z time t is equal to minus summation yi ai, where I goes from 1 to n is the total number of neurons, and we saw that in the simplified form this can be written as minus I summation I comma j minus half summation I comma j uh, mhm, wij yij minus summation biyi. This goes from 1 to n, this also goes from 1 to n. Now let's see what happens to the, and this y's are at the time t. So if let's say I start at time t equal to 0, the energy of the Hopfield network at time t equal to 0 is equal to, you will see, if you open this bracket, is minus half into w11 y1 y1 plus w12 y1 y2 plus w13 y1 y3 plus w14 y1 y4 plus w21 y2 y1 plus y4 w44 y4 y4 to y4 y4, and the bias, the b's, we consider to be equal to 0. Then if I use this w matrix that we saw earlier and the y matrix at time t equal to 0, this entire thing is at time t equal to 0, then we can see that E of y bar at time t equal to 0 is equal to 0. Now at time t equal to 1, if I use w's, w is a constant in time, and I use y1, that is y, the matrix y, at time t equal to 1, then I will see that my E of y bar at 1 is equal to minus 6. Now, if I go further at time t equal to 2 and use the same weight matrix and use the uh, y vector which we found at time t equal to 2, then we can again see that this will be equal to minus 6. I'm not doing the calculations, it can be easily done. So if I plot the energy of this particular Hopfield network over time, I will see that it goes something like this. So if this is 0, this is 1, and this is 2, it will drop to minus 6 and remain in this forever. So this is the stable equilibrium point energy value. Stable equilibrium point energy value for this particular Hopfield network. We will later see and derive in general how uh, the energy of the Hopfield network upon successful iterations always decreases, and some other another interesting uh, properties of the Hopfield network.